Hello dear students, welcome to the TEQIP Faculty initiative of Let's Crack the Gate. So today we are going to start with the today's class, that is power electronics, and today's topic is 3-phase AC/DC rectifiers. So before beginning with 3-phase AC/DC rectifiers, let's have some brief concept of 3-phase supplies. All right, because it is required, it is necessary to understand the working of a 3-phase rectifier. All right, so let's have a quick revision of 3-phase supplies. So as we know that 3-phase supplies we talk about, first of all we have to know that a balanced 3-phase supply means it should be balanced in magnitude as well as in phase. Okay, so magnitude means all the magnitude must be same, and for 3-phase system all the phase must be 120 degree apart. All right, so like this, if we talk about this, it should be like this. This is phase A, this is B, this is C, and I am drawing here the reference phases, that is phase voltages. All right, so I am taking AN as the reference phase. All right, another important thing is that you must determine what is the phase sequence. All right, so phase sequence, here we can see how to determine phase sequence, that you stand anywhere arbitrarily and just see in anti-clockwise fashion which phasor is coming first. All right, and after that which is preceding that, and after which is coming, which is following them. So if you see here, let's say first CN phasor is passing, then AN phasor is passing, then BN phasor is passing, then again you will see CN phasor is passing, then again you will see AN passing, then BN, then again CN, and it will go on. So if you see what is the phase sequence, it is repeating like this: ABC, ABC, ABC. So here the phase sequence is ABC. So this is how we see the phase sequence. So here let's say, so as I mentioned in my previous lectures also, I mentioned that it is very important to have some reference value. So I am taking reference as A phase. All right, so I am taking phase A as the reference. Please keep this in mind, because unless you don't define the reference, especially in 3-phase circuits, you will not be able to determine how to calculate the output voltage or whatever things. So you will see in the means as the lecture will continue. So let me define that. Let's say that VAN is the phase voltage, that is reference van, and I am taking it as Vm sin omega t, or in phasor domain you can take it as Vm angle 0. So obviously VBN will be, if you see here, it will be minus 120, and here it is plus 120. So VBN can be written as Vm sin omega t minus 120, or in phasor domain it will be Vm angle minus 120. And what is VCN? It is Vm sin omega t plus 120. All right, or in phasor domain it must be Vm angle plus 120. So when 3-phase supplies are there, we know that we have got 3 phases and 6 line voltages with them. All right, so we have to draw the 6 line voltages also, we have to understand them also. So I am drawing the phasor diagram. You please note that this phasor diagram which I am going to draw here is very important. All right, if you can understand this phasor diagram, then it will be very easy to understand the power electronics. You don't have to draw the phasors again, this waveforms again and again. Obviously for some purpose it is required. So I am showing you how this is working. Okay, so let me have this, and another circle I am taking. Okay, so now you see here, if I am taking this inner circle is representing the phase voltage, means which are circulating, and the outer circle is representing the line voltage which are rotating. All right, so I am first making the phase voltages. Okay, so this is my A phase, this is my B phase, and this is my C phase. Okay, no problem with this. And you know that if you are going to draw the line voltages, how you draw the line voltage? It is simply, we know that VAB means it's VA minus VB, or VAN minus VBN. Okay, and VBA means VB minus VA, or VBN minus VAN. Okay, so now here in this case, if you see here, that it is simply means just we have to subtract two phasors. Alright, so and how to subtract, that you already know, that we have to reverse one phasor and then add them. So here if you reverse them and add them, you will get like this. Okay, so see, you get VAB here. So this is your VAB. Alright, VAB. So now you want to write VAB. So every value, and why I have taken this reference? Because each and every value I will represent with respect to this A phase. That's why I have taken this as reference. So please note this. So if you write VAB here, what will be the VAB value? It will be, now we know that in line voltage magnitude, here you see in phasor domain we have magnitude and we have angle. Alright, so you know that magnitude become √3 times. Alright, if for its derivation you can please refer to this basic electrical engineering course. For here you can also write them as VMP, where P subscript represents phase, peak value of phase. Alright, it is important to represent like this. So here you can write VMP, and angle, you know that this angle comes around 30 degree, positive 30, because angle anti-clockwise. Alright, so it will be plus 30 degree, or in other words you can also write it as √3 VMP sine omega t plus 30. I am writing one line voltages. In the similar fashion you can write all of them. Alright, or in other words you can also write them as VM line, where L represents line voltage, peak value of line voltage. VM line sine omega t plus 30 degree. Okay, so similarly we can draw other phasors also. So this is, if you draw here, so it will give you VAC. So here it comes minus 30 degree. Okay, you can refer to basic electrical engineering for this. Alright, so here you can see VAC is √3 VMP angle minus 30 degrees, or in this terms you can also write like in these terms also. I am not writing here, you please write it in terms of this. Alright, then again we have C here, minus C here, and if you take reference means add these VBC, so you will get here VB is positive, C is negative, so here you will get VBC. So here if you see VBC is √3 VMP angle minus 90. Alright, and here you can see this is minus A. So if you take its value, this, so obviously this VAB means it is opposite of VBA, or VBA is opposite of VAB, whatever way you want to put it. So it is VBA. Alright, so if you put VBA, so how will write VBA? It's very simple, just since it is opposite, so what you have to do here, just subtract 180 degree from VAB value, because it is just opposite now, that's why. So just subtract 180 from here, so you will get VMP angle minus 150. You see here. Alright, just subtract this total is 180 from here, from this point to this point is 180, and here you have already got 30 degrees. So what is left with respect to A? That is minus 150, and then we have got this. This value is what? A negative, C positive means VCA. Alright, so obviously it must be opposite of VAC. So VCA, how will write its value? Magnitude will remain the same, √VMP, and what will be the angle? VCA. Yes. So what you have to do, since it is negative here, so what you do? You just add 180 degree here. So in this case, if in VAC add 180, you will get what? Plus 150. If you subtract 180, you will get plus minus 210. Alright, and then last that is VCB. VCB. So we have got VCB here. Okay, so what is the value VCB here? It is root 3 VMP. Here also just add 180 degree. So you will get minus 90 plus 180 means plus 90 degree, or from the geometry point of view with respect to A, you can also find all these angles. All right. So what we are seeing here is that now what you have to do, that after writing these phase line voltages, if you both of phasors are rotating anti-clockwise with some omega speed, so we know that the phase voltage sequence is VA, or in terms just simply write ABC. Phase sequence is ABC. If you want to write the sequence of line voltages, then what is this? Let me see the live chat also, what people are asking. Okay. All right. So here, if we write this line voltage sequence, you can write. So here the same procedure as I have explained in the finding the phase voltage sequence. Similarly, you can find the line voltage sequence. So if you find the line voltage sequence, what is the line voltage sequence here? It is AB followed by AC, then BC, then BA, then CA, and then CB. Okay, this line voltage sequence it follows. All right. So we have to remember this ABC. If phase sequence is ABC, then line sequence is this. If you don't have to cram it, you just remember what is the phasor diagram. All right, from that you can just derive it. All right. So we have got AB, AC, BC, BA, C, and CB. But this is true only if the phase sequence is ABC. If I change the phase sequence, that is ACB, one time GATE people have done this. They have given ACB phase sequence. All right, and based on that, they have to draw the output voltage waveform and then find the current and voltages or everything. All right. So it's just a matter of representation. All right. If you talk in terms of if you talk in terms of this, all right, in terms of this, there is no difference at all. So now means after having the little quick knowledge of three-phase system, let's start with the three-phase rectifiers. All right. So when we go for the three-phase rectifiers, first of all we will start with three-phase half-wave rectifiers. Okay, three-phase half-wave rectifiers. All right. So this is very important to understand, because until you don't understand half-wave rectifiers, it will be very difficult to understand the full-wave rectifiers. All right, because full wave is the cascaded structure of the two half-wave rectifiers. All right. So when we talk about the three-phase half-wave rectifiers, we have got two types of connection. First is called common cathode connection, and another one is called common anode connection. So what is common cathode and common anode? If you take any controlled or uncontrolled device, means let me take either diode or let me take either thyristor. All right. We know that it is anode, it is cathode. Here it is anode, it is cathode, and it is gate. So what is meaning of common cathode connection? Common cathode means all the cathodes of all the switching devices are at same potential. All right. And common anode means all the anodes of all the switching device are at the common, their anodes are at the common potential. So let me start with the first one, that is common cathode connection. So if you start with the common cathode connection, so let's draw its figure first. So here you can see, I am first of all explaining with the uncontrolled circuits or uncontrolled rectifier. After understanding uncontrolled one, then we can proceed for the controlled one also. So this is three-phase supply, this is VAN, this is VBN, this is VCN, here it is IA, IB and IC. These are 3 source currents of the 3 different phases. Alright, all the 3 source currents will be same. Alright, and but only difference is their phase. So this is common cathode connection. You see here, all the cathodes are at same potential. Okay, and let me mark it as DA positive, DB positive and DC positive. The purpose of marking like this is for our understanding, for our clear cut understanding. So here it is load, any type of load we may have, and here it is neutral point. Okay, so here we have the means output voltage from, if you say that this is my reference output voltage and this is my reference output current. So you can see that load, output load is taken between any phase and neutral. Alright, you can see here clearly that the output is taken from any load voltage, sorry, any phase voltage and between neutral. So here you can also write it right, PN. Alright, PN means any phase to neutral you are getting the output. And why I am writing plus sign here, for as I explained, for our understanding, it means that in common cathode connection what happens means, since the cathodes are at same potential, means what will decide which switch will turn on or which switch will become more positive, that will be decided on the basis of what is the phase voltage value across the switch. Alright, so it means in simple terms we can see, if you remember in the single phase also I have explained that in the positive group which thyristor or which diode will turn on, the most positive diode or most positive thyristor will get forward biased. So similar in common cathode connection also, the switch, I am writing switch means I am writing a general statement, either use diode or use thyristor. The switch which is at highest potential, highest positive potential will be turned on. Highest positive potential will be turned on. Okay, it means that what we have to see across the diodes. Alright, in first way it might seem that we have to see the phase voltage across the diode. No, it's not true, because once the current starts flowing here, alright, why I am saying the phase might be seen only in case of if the load current is 0. Only in that case we have to see which switch is, which means we have to see the phase voltage across the switch. But otherwise we have to always see the line voltage across the switch. Whatever the line voltage is getting forward by means positive, most positive across any switch, that switch will get turned on. How is it that? Let me show you with some example. Alright. For example, if you say the diode DA is turned on by somehow other, diode DA is turned on. So if diode DA is turned on, what will happen? This diode will be shorted. Alright. So once this diode is shorted, immediately this phase voltage will come to this point, this P point, this phase voltage will A will come to this P point. So when this A voltage will come to this P point, now here you see at this P point what will be the voltage now? Here load voltage will be phase voltage. Alright, you can see here, because load voltage is collected from P to N, that's why load will be equal to phase voltage. Here you can also see if your diode is short circuited, this load is coming in parallel with A phase. Alright, but what is happening across DB positive and DC positive? Here you can see if you write A voltage here, so what is happening in the diode? Let me mark like them now. So what is the potential across diode DB and what is the potential across diode DC? You see at plus side it is B potential, phase B, and minus side A voltage. So what is the potential across DB? You can see it is basically BA. And what is potential across diode DC? It is CA. So which diode in the means circuit will be next to conduct? So which diode will be next to conduct, that will be decided on which line voltage is going to be most positive. So let me draw a table here which will make you understand very clearly. Now you see, if you see that if diode, any diode is conducting, means we can see that conducting switch and voltage across other diodes or switches, rather right, switches. So let's say if the conducting diode is dA positive, so what will be the voltage we are getting? What is the voltage? We can see here, when the dA is positive, then output will be, and here we can also write what will be the output voltage, V naught. If dA is conducting, we know that the this a P point and N point will come in parallel to A and N. So obviously the output will be AN, VAN. And what is the voltage across other switches? You can see that when A is on, here P will be having the A potential across it, and diode DB, what will be the potential across it? Here B is positive and A is negative, means what is the potential line voltage across diode DB? That is BA. BA potential is there, and another potential which we have, which we get across diode DC positive is C is here and A is here, means VCA. Alright, plus first of all fill up this table, okay. Then you see we have got diode DB positive. So if DB positive means if diode B is conducting. Now how now someone may ask that how you have decided that diode DB positive will turn on. You can see here. So for that purpose we will move to the phasor diagram here. So you can see that in the phase sequence, means phase sequence represents that how the means voltages will become, in what sequence positive voltages will come. Alright. So here you can see that first AB voltage peak will come, then AC will, then the positive voltage of AC will come, then the positive of BC will come, then positive of BA will come, then positive of CA will come, then positive of CB will come. So here you see what voltages we are getting VBA and VCA. So here you see VBA and VCA, means who is preceding? BA is preceding now. So if BA is preceding and CA is after BA, so it means which diode has the possibility to get turned on after A? That diode B. Alright. So diode B have the possibility, when the diode A will become reverse biased, after that diode B has the possibility of, or means chance of getting turned on. So in this way we see how which diode or which thyristor is going to turn on. So now you can see when diode B is turned on, what will happen? Now if B is turned on, obviously with the turning on of B, A will be turned off. So if A is turned off, now what will be the potential at P point? Then the potential will get at P point is B. So when you get the potential at P point as B, then the output voltage will be, now you see that now the load voltage is in parallel with the BN potential or VBN, because A is not, DA positive is not turned off. Alright. So it means output will be equal to VBN. And now if you want to see what is the voltage across other switches, now A is also off, C is also off. So you see here A is positive and B is negative, here C is positive, B is at negative terminal basically. So what voltage here we are getting? Here we are getting VCB and you are getting VAB. Now again the question arises, which diode is next in line, or which switch is next in line? So which switch is next in line? Again see this line voltage sequence. So what is there? It is CB, then again you can write AB. Alright. So if you see here, which is next in line? CB then AB. It means first CB will be positive, then after CB AB will follow. So it means which diode has got the chance of next conduction after B? It means C positive has got that conduction chance. Alright. Please understand this concept here only, very nicely, because otherwise if you somehow other not understood the concept here, then it will, you will face very much difficulty in understanding the concept in full way. All right. So now the C positive has got the chance. All right. So when C is already on, so with C turning on, B will be negative and B will turn off. So if B will turn off, now here at P point we have got C. So now the load is in parallel with the VCN. Okay. So output will be equal to VCN. And now what are the voltages across other two diodes? You see here A is at positive, C is negative terminal. Here B is at positive terminal, C is at negative terminal. So here you are getting the two voltages. What are those? VAC you are getting and VBC you are getting. So now again you see which diode has got the chance to conduct next, which diode will follow after C positive. C, you have got VAC and BC. See here, AC is preceding BC or BC is following AC. It means AC will become positive earlier than BC. It means which will have the chance next. The next chance again the diode DA positive will have. So in this way you can see the output means this diode will conduct in the sequence of DA positive followed by DB positive followed by DC positive. Okay. Now if somehow other you change this phase sequence. Now if you, instead of taking ABC sequence, if you take ACB sequence, then this diode conduction sequence will also change, this table will also change and this output voltage will also change. Okay, you please remember this thing. So phase sequence has very deep effect on the working of the rectifiers, AC/DC rectifiers. So now let's understand the waveform. So as I have written for the DA means diodes, similar is true for the thyristors. So similar you can also write it for thyristor A, thyristor B and thyristor C. The only thing here the only difference will face or you will see is that diodes will immediately turn on or turn off. Okay, as soon as they get forward bias, they will immediately turn on. But with the thyristors, until unless you don't give them the gate pulse, they will become forward biased, but they will remain in forward blocking mode. They will not conduct. So with the thyristors, the only difference comes with the firing angle. All right. So let's start with its waveform. So I've already drawn the waveform in MATLAB, means only the three-phase waveform. So I'm copying it from there. You can see here I've already drawn this waveform. So let me copy this waveform. Yes. Okay. So here you please see, you please don't get absorbed or don't get lost in the waveforms. Okay, please don't do that. All right, or especially in this 6-phase waveform. So what do you do now? What you see here? Here, if you see, let me hide this much portion of the waveform. Okay, I am showing only the positive half. Okay. So in the line voltages I am showing only positive half, and in the phase voltage I am showing the both. So here you can see this upper one you are seeing is the phase voltage, and the lower one you are seeing is the 6 line voltages. So what are these? Just recall this phasor diagram again and you will be able to understand. I have taken the phase sequence as ABC, and the line voltage you can see the 30 degree plus 30 degree means VAB is plus 30, VAC is minus 30 with respect to phase A. So you can see this blue one is phase A. Let me mark it. Yes. So this blue one is phase A, AN. You can see this green one. All right. This green one is BN because green is minus 120. So you can see it is minus 120. Okay, you can observe it. And this red one you can see it's what you see. if you see here, it is minus 240 or plus 120. So this red one is VCN. Okay, so you see the phase voltages VAN, BN and CN. Similarly, now we have to mark this the line voltages also. So for line voltage, you can see if you try to mark here, it will not be possible. All right. So again, I am showing you again only the positive halves. Yes. So you can see this this yellow one here. This yellow one. This yellow one is starting just from 30 degree. Now from where you have to see the 30 degree difference. We have to see this 30 degree difference from 0 with respect to phase A. We have to see the voltage with respect to phase reference. And what reference we have chosen? We have already chosen A phase as the reference. You can see here that we have chosen A phase as the reference. Okay. So with respect to A phase, the AB voltage is 30 degree, AC voltage is 30 degree lagging. See here, AC voltage is 30 degree lagging. So it's easy to identify AC. All right. And with respect to A phase, this AB voltage is 330 degree lagging, either 30 degree leading or 330 degree lagging. So I am writing in terms of, let me write here in everything in terms of lagging. So here you can also write it as root 3 VMP angle. This will become this minus 210 degree. It will become root 3 VMP angle at 70 degree, and this will become angle minus 330 degree AB1. All right. So now with respect to this, now it will be easy to identify. So you see here this yellow one is representing 30 degree with respect to A. You can see here that this is 30 degree, and please note for one thing that means this phase voltages or three phase voltages, these cross at the multiple of 30 degree, cross each other at multiple of 30 degree. You see here, this is 30, this is 90, this is 120, this is 30, 90, 120, and what this value is again. In this way you can find out what this value, this is 210. All right. Then this again, in this way you can find out. All right. And where the two waves cross, on the opposite side there is a peak of third wave. All right. You see here in each and every case. So you can easily find out what is the value of this, where the wave is crossing. It's very easy. How you can find? You know the nature of the curve. If you see, if you take VAN, let me take VAN. So VAN is VMP sine omega t. And what is omega t at this point? At this point omega t is 30 degree. So you can write VMP sine 30, and sine 30 is 1 by 2, means 1 by 2 VMP. It means at this point the value is VMP by 2, because if you see this peak value is VMP, if you take peak value as VMP, then this 30 degree crossing will give you VMP by 2. Okay. Similarly, you can find here also in this line voltage also, but let me first mark all the line voltages. So this yellow one is representing AC. Okay. From this 30 degree we can easily identify. Then after that, just remember the sequence. What was the sequence? I am again writing AB, AC, BC, BA, CA, CB, again AB. Okay, this was the sequence. So just see, after AC 60 degree lagging. What is 60 degree lagging voltage? That is, and you can see from the here also you can see, please see here that in AC and BC there is the difference of 60 degree, and in BC and BA there is a difference of 60 degree, means each line voltage is 60 degree apart. Okay. So you see here, so after 60 degree what is next? Green voltage. You see the green one. So this green one is your BA. All right. And then after BA, this green one, there is light blue one, this one. So this one is CA, and after that we have got red one. Okay, you can see red one. All right. So this red one is AC, BA, AB, AC, sorry, it is BC, not BA, AC, BC, and this one is BA, and after that it is CA. Let me write it more proper. Yes, AC, this is BC, then this is BA, then this is CA, and after one that it is CB, and after that it is AB. So, you can conclude that this dark blue one is AB. So, here also we can mark it here, this is VAB. Okay, it's clear now. Alright, and another thing, I am already showing you the positive cycles, because obviously means if AB becomes positive, obviously BA will be negative at that time, and when AB is negative at that time, BA will be positive. You can see here also, very easy to understand. You see dark blue is AB and light blue is BA. You see at the from this point, from 0 to till the point here, this dark blue is positive, and in the same time this light blue BA was negative, and when BA became positive, the AB became negative. So, it is very simple. Alright, so don't get absorbed or don't get lost in these waveforms. So, let me start with the circuit. What will be the output voltage and what will be the voltage across diodes. Alright. So, let me start with the resistive load. So, if you take the resistive load here, okay. So, I have already explained. So, please refer to this switch table also. So, it is better to refer to this. So, when you refer to this switch table, what is happening here? Let me have some other color. Okay, let me choose this. So, what is happening here? So, you see here when diode, now let me explain one more thing. Yes, if you talk about 0 to this point, 0 to 30 degree, alright, you can skip also this point, because 0 to 30 degree, if you are starting the operation just now, we are not considering that this switch was already conducting. We are not taking the case as written in the books. I am just starting with the starting cycle. So, with the starting cycle, if you see, if the output voltage is 0, let me say that the output voltage was 0. Okay, let me rub all these things. Oh, sorry. Yes. So, if you see, say that the starting voltage was 0, so in that case, or load voltage was 0, what will happen from 0 to 30? In that case, if I already told you, if the current is not flowing in the load, in that case, the phase voltage will decide. Okay, if the current is not flowing in the load, you please catch these concepts very clearly. Only if and only if current is flowing in the load, then only the switches will experience line voltage across them. If the current is not flowing in the load, or load is disconnected from the source in any form, in that case the phase voltage across switches will decide which will turn on, and that happens when current was discontinuous or output voltage become or at the initial of the cycle. So, you see at the initial of the cycle that from 0 to 30 degree AN voltage is less and CN voltage is more. You see red one, CN voltage is more and AN voltage is less. So, it means at the starting of the cycle this AN is less positive and CN is more positive. So, which has got the possibility to turn on? You please remember the concept of this concept I have already told you in the single phase full wave rectifiers, that in positive group that will turn on which is most positive, and in negative group that will turn on which is most negative. So, see here in 0 to 30 degrees C voltage is more positive and A voltage is less positive, although both are positive, but only one can on na. So, it means C will get turned on. Alright. So, as soon as C will get turned on, even if A is positive, but because C is more positive, hence more positive will be applied across the negative terminal of A, hence the A will become negative, alright, or reverse biased. You see here, although A is positive here, But when C is more positive, so what will happen? I am drawing A positive voltage here. So here at plus terminal, this minus terminal. Here already A is applying and here C is applied now. So although A is also positive, but C is more positive. So what will happen? Ultimately this diode will become reverse biased. So which diode will turn on from 0 to 30? That is C positive. And when C positive is turned on, obviously output will be VCN. Okay, so output will be VCN. So let me mark here. So output will be VCN means this one. So CN is like this. So you will get output like this. Okay, from 0 to 30 degree. Now what will happen? After 30 degree, what is happening? Now you have to see, once the process starts, now the current has started flowing. Alright, you are agreeing with this? Now if the current has started flowing, now there is no need to see the phase voltage across the devices, because if now you see the phase voltage across devices when the current is flowing, you will get the wrong answer. Alright, so now you have to see the line voltage. So once C has started conduction, what are the line voltages? VAC and VBC. So which will conduct? VAC. VAC means which diode will means VAC was across which diode? It was across DA positive, and VBC was across DB positive. So which is going to conduct? Now A positive is going to conduct. It means when A positive is going to conduct, so as soon as A positive is going to conduct, the C will get reverse biased. Why? One, you can see that already the output also is becoming negative, but the means real answer lies in the output, this line voltage, because line voltage AC, this line voltage AC is becoming positive here. Alright, line voltage AC is become positive here across diode A, and that's why the C will turn off. So from 30 till what point A will remain on? Till the favorable condition for B arises. Until unless the favorable condition for B arises, till that point A will remain turned on. So now if A will remain turned on, so it means what will be the output voltage here? See here, what will be the output voltage if A is turned on? AN is the output voltage. So let us mark here. So you have got AN. Now here you can see, one can ask, sir, how you have decided that it will go up to this point? You can see through the line voltage. See here, when A is conducting, who is in the line next? See here, when A is conducting, voltage is VBA and VCA, where VBA is across DB positive and CA is across DC positive. You just see when BA is becoming positive. See here, BA is becoming positive here at this point after 120 degree. See here, after 120 degree, BA is going to be positive. So before that, who is going to conduct? A is going to conduct. Alright, that's why I have marked from here to here. Okay. So now at this point, now you see that at this point, this diode B has started conduction, because now BA has become this line voltage BA has become positive. See here, you have for learning 3-phase, you have to simultaneously see phase and line voltages. Alright, so you see here, now BA has positive, so becoming positive, so it means what will be the output? Now diode DB is conducting, so output will be VBN. So just draw output will be VBN. So although output is a phase voltage, but who will turn on is decided by the line voltage. So now you see, when B has started conduction, so what is the voltage across? What are the two voltages? VCB and VAB, where VCB is voltage across C positive and VAB is the voltage across A positive. Alright, it is across C positive and A positive. So now you see who is next in line. See in the sequence, next in line is CB, but from where CB is becoming more positive? See here, CB is becoming more positive after 120 degree of BA. See here, after 120 degree of BA, CB is becoming more positive. So it means from this point C will conduct. So when C will conduct, what will be the output? CN will be the output. So let us draw. And again, as C will conduct, what will be the line voltages? That is VAC and VBC. And what are the line voltages across which diode? AC across DA and BC across DB. So he is going to be next in line. You know that AC is preceding then BC. So next in line will be again DA positive. Alright, and when A will conduct, then the output voltage will be again AM. So in this manner you will get the output voltages. See here. And since it is a resistive load, the load current will also be similar to this, okay, because it is resistive load. Okay, all right. Now next question arises, what will be the voltage across device? So that is not a very big question. Why it's not a very big question? Because you already know, if you let's say if you want to find the voltage across DA, I am finding voltage across DA. Let me write it, that we have to find V DA positive. Okay, so voltage across DA means when the switch is conducting, the voltage across DA will be 0, and when the switch will be reverse biased, the voltage across DA will be whatever it is. So let me see what is that. Okay, so you see at what instance A was off and at what instant A was on. So you see here, A was on, which green one I am marked. So A was on from 30 to 120, means when AC voltage was there, all right, when AC voltage was there, A was conducting. So during that period, the voltage across A was 0. So and this is for only for 120 degrees. So means from this point to this point, the voltage across A was 0. Agreed? All right, you can see through the table also. All right, because and from the figure also, from 30 to 120 degree A was conducting, hence voltage across A was 0. Now A was off when B was conducting and C was conducting. All right, but you see when B was conducting, voltage across A was different, and when C was conducting, the voltage across A was different. So you have to be very careful with this. All right, so when B was conducting, voltage across A was VAB. So we have to mark VAB, and this obviously must be negative. So VAB is what is VAB? You see here, dark blind. So what is VAB? Just mark it. You see here. And till what point? Till it go till here? No, it will not go here, because at 120 degree, after 120 degrees C was conducting, so it will go up to only 120 degrees. All right, it will go only up to 120 degrees. See here, let me rub it and mark it again. See, it will go up to 120. Why up to 120? Because at this instant now C was conducting, and when C was conducting, voltage across A was VAC. So see, what is VAC? This yellow one. So from this point and till what point? Again till this point, because again from here A is conducting. Okay, and then again A was conducting till 120 degrees. Till 120 degrees, and again like this. So in this way, so one practice you have to do is that you have to be very accurate in drawing the three-phase waveforms. You must practice drawing the three-phase waveforms. All right, then only you can understand. Now question arises, if you want to calculate what should be the values? It's very easy. Since this is peak value, you can see here, this is peak. I am marking the negative peaks. Similar is true for the positive peaks. So this negative peak value is VM line. Okay, this negative peak value is minus VM line. Okay, now if we want to, if I say you calculate this value, this one where the crossing is taking place, this value. So how you will calculate this value? So it is very simple. It's not very difficult task. You must know two things only. First of all, you must know what is the nature of curve, means it is whether root 3 Vm line sine, root 3 Vmp sine omega t plus minus phi. This kind of nature you must know, and what is omega t value is there, you must know that. Okay, with these two things you will be able to find whatever point you want to get. Alright, I've already marked that. If you have seen the video, I've already marked it here in the phase voltage. Alright, so in this way we have to continue with the 3-phase rectifiers. So you see here, it's very simple. Alright, now instead of resistive load, if you take a RL type constant current load, alright, if you take a constant current load, again you can see, since it's a diode, hence it doesn't matter means what kind of load you take, because ultimately the output is going to be like this. In case of diode rectifier, uncontrolled diode rectifier, output voltage will be same. Alright, and hence that voltage across device will also be same. Now the only difference will be in current. Yes, so now let's draw the source current. So when you are going to draw the source current, you please remember you have to draw only one phase current, only single any phase current. Either draw A phase current, B phase current or C phase current. You don't have to draw all the three. Just draw one phase source current, and after that is means other source currents will be 120 degree shifted. Same shape, only shifted by 120 degree. So if you draw the source current for a resistive load, so let me draw. So it's very simple. So if A phase is on, if diode A is conducting, then only A phase current will flow. If diode A is off, then the A source current will be 0. Similarly, if diode B is on, then only the B source current flow, otherwise it is 0. And also you see that since the diodes is a unidirectional device, hence source current will only be positive, it will not be negative. Alright, the source current will only be positive here. Alright, so let me draw the source current. So I am drawing source A current. So if you draw source A current for resistive load, obviously you know the source current will be same shape. So I am drawing the source current for the constant current load of I naught. So what will be that value you see here? If you see, it will start from here, this point to this point, means from omega t equal to 30 degree to omega t is equals to 150 degree, the source current will be there. After that, for you see, for 120 plus 120, for 240 degrees, the phase A current will be 0. Why it is 0? Because diode A was turned off. You see here. Alright, I am drawing A phase current. Alright, and after this, you see here, again since this green one, again A is conducting. So see, source current is flowing, and again after that for next 240 degrees it is 0. See, like that. Okay. So again, after finding all this source current for constant current load, again one thing you have to do is you have to find its Fourier series analysis, and after finding Fourier series analysis you have to find displacement power factor, you have to find power factor, and you have to find THT. Alright. So before that, now let us find out its average output voltage. What is that? So finding the average output voltage, what is the time period here? So you can see that it's a 3 pulse rectifier. Very simple to see. How you will see here? In input wave of this is input wave. See here. This is the input wave from 0 to 2 pi here. See here. In this one input cycle of 2 pi, there are 3 output cycles, complete output cycles. See here. This 1, 2, and here from up to this portion, and the rest of portion completed from here. So you see, in the input cycle, one input cycle, there are 3 output cycles. Alright. So that's why what is the time period? It's again 2 pi by 3. How it is that? Total input cycle is 2 pi. Alright. Total time period of input cycle is 2 pi, and how many output cycles are there? 3. That's why 2 pi divided by 3. So what is the time period? It is 2 pi by 3. Okay, so simple to find out. Hence, and since one input cycle contains 3 output cycles, hence it is also known as 3 pulse rectifier. Okay, it is also known as 3 pulse rectifier. Okay. So now you have got the T. Now you can see whatever limits you here, especially in 3 phase, you have to take care of limits very carefully, because if you change the limits here, your curve will also change. So if you say that I will take this blue one, I will take Bn, then you must take the nature of Bn also. Alright, let me show you that I am calculating V naught average, thick, and I am taking VBN omega t. Alright, so obviously I will, if I am taking VBN, so I will put limits here. Alright, it is 150 to 270. Alright, 150 to 270. So what is 150 termed as? 150 is termed as 5 pi by 6, and 270 is termed as, I think, pi plus pi by 2. So what is that? Pi plus pi by 2. 9, no, yes, pi plus pi by 2. So 2 pi plus pi, 3 pi by 2. Yes, it's 3 pi by 2. So now you have to see, you have to take the VBN value. So if you are taking the limits from 5 pi by 6 to 3 pi by 2, it's very important in 3 phase rectifiers. So whatever limits you are taking, you have to see between those limits what curve you are getting. So I am getting VBN, that is VMP sine omega t plus, no, not plus, minus 2 pi by 3, minus 120 na, that's why. So it is here. So just solve it. V naught average, that is VMP take out, and what you will get here, and 1 upon t also, 1 upon time period also. So 1 upon 2 pi by 3. So here it will be 3 VMP upon 2 pi, and if you solve it, it will be minus cos omega t minus 2 pi by 3. I am putting the limits of omega t, so that's why. So that is 5 pi by 6 to 3 pi by 2. Just put the limits, you will get 3 VMP over 2 pi minus cos, you put 3 pi by 2 here. So it will be 3 pi by 2 minus 2 pi by 3, means 270 minus 120. So 270 minus 120 is 150. It will be minus cos 5 pi by 6. Yes, 5 pi by 6, and plus cos, you now put 5 pi by 6, 5 pi by 6 minus 2 pi by 3, 5 pi by 6 minus 2 pi by 3, it is means 150 minus 120, it is simple pi by 6. What is that value? Just calculate it. You will get V naught average is equals to 3 VMP upon 2 pi, and cos pi by 6 is root 3 by 2 minus, what is cos 5 pi by 6? Just calculate. You know that cos 5 pi by 6 is also root 3 by 2 minus root 3 by 2. So it will be plus root 3 by 2. So what value will get here? Yes, so you 2 will be cancelled out, 2 root 3 by 2 here. So it is 3 VMP upon 2 pi into 2 root 3 upon 2, 2 will be cancelled out. So what is the average output voltage in case of this? That is 3 root 3 VMP over 2 pi. So that is the average output voltage for diode rectifier. Alright, and in case of diode rectifier, no matter you take resistive load or you take continuous current load, you will get the average output voltage as this only. Alright, so now next comes this